Well, hello everybody. We're going to be talking about Whitney's bike ride, and our goal here is to connect position, velocity, and acceleration, which we already know quite a bit about using integration. So here we have a picture of Whitney's bike ride. Whitney and Aunt decide to get together to do calculus homework. Whitney rides her bike along a straight road to get to Aunt's house. At time equals 0, Whitney leaves her house and she arrives at Aunt's house 24 minutes later. Her velocity in miles per minute is given by the graph on the graph shown below. So this is v of t. And so we want to know her acceleration at time 9. So 9 is right here-ish. And so that would be, and so what we're looking for, since we want acceleration, we're looking for slope at 9. And it looks like the slope is -2 over 1. Now, I always used to get very confused about what was going on here. And actually, let me back up. That's probably wrong. I would get really confused about what was going on with the units. So it's down and right, and I'm just going to go with the squares I see. That's where I got 2 and 1. But then when I look again, I'm like, oh, it was down from 0.6 to 0.2, which is down 0.4. And it's right 2 squares from 8 to 10. And so, but if I work through this, moving the decimal in one place, we've got -4 over 20. And so that actually becomes -1 over 5, or -0.2. So I was incorrect, and it's really important to pay attention to units. And so it's -0.2, and that's miles per minute squared. Miles per minute squared, or minutes per minute, whichever way works better for you on that. Then, at some point in her journey, Whitney realizes her luckily calculus pencil just fell out of her pocket. At what time did she come to this realization, and how do we know? So I went ahead and grabbed the picture of the graph so I could keep looking at it. Yours, of course, is on the same page. Her calculus pencil fell out of her pocket, and how do you know? Well, we know what happened here, right here, is so we can see her velocity is increasing, it's staying constant, and then it's slowing down. And then right here, her velocity is actually equal to 0. And since her velocity is equal to 0, that means she's stopped. And then her velocity is negative here and here, which means she's going backwards. So this is when she realizes she lost her pencil, and this is when she found her pencil and turned back around going the other direction. So those are the two things. We also know her velocity is 0 when she starts and 0 when she finishes. Both of those make sense. But so we're just looking at the zeros. And I'm going to say at time 9, excuse me, at 11 minutes, velocity is 0. And it changes from positive to negative. And you'd want to use words for that, not symbols. Which means she goes from going quickly to going slowly, which is why she's turned around and looking the other direction. Not going quickly to going slowly, excuse me. Going forward towards her friend's house to going backwards. So she's backtracking here, and she's backtracking for 1, 2, 3, 2, 4, 5 minutes. And then she's going back to her present's house. How far apart is Whitney's house from Aunt's house? Well, it took her 24 minutes to get there. And so to find this, we want to find the net distance. What we're looking for. So how far did she travel? And so what's nice about this is if we take the integral from A to B of her velocity, we'll find out how far she went. And we're talking displacement. And so this backtracking will go away. And then when she overlaps, so like she's backtracking here, and then she's traveling back across where she already went. But by doing it this way, we will remove that backtracking. and then the doubling up. So it'll go, we'll subtract, add and subtract. So when we look at the picture, we've got triangle, I'm going to just do a trapezoid. It's easier than doing the two triangle. I'm going to do a trapezoid, a triangle, and a triangle. And so I'm going to go ahead and move this picture down and move the kind of the notes I put on already. Get it out of my way for a minute. And so, like I said, I'm going to do a trapezoid plus two triangles. Well, actually minus one triangle. And so I've got 1/2 base of 11, base of 3, plus 0.8, which is how high up she is. That's the height. Oh, times 0.8, excuse me. Minus this triangle here, 1/2, 5 times 0.6. And that is not a negative height. It's, yes, it's going down, but we don't count that high as negative. Plus this triangle up here, 1/2 of 8 times 0.6 as well. Okay, and that is equal to 6.5 miles. And while we will be using a calculator later with this question, we want to try to do it without a calculator for as long as possible. Okay, so that's B. Now for this one, what is the total distance traveled? So if you recall, this distance is backtracked and we've removed it right here, which takes care of the, I traveled backwards for 5 minutes and backtracked and looked and found something. This is when she found her pencil. This is when she gets back to where she started. Okay, so she's found her pencil, back to where she started. Realized she lost it because she turned around. Possibly realized she lost it here. But, you know, whatever. So, total distance traveled. So total distance is a little different, and this is the key to really this lesson, is the difference between net distance and total distance. So net distance is just the integral of velocity because it gives you a position. That's your, if you think about it, this is what we were calling displacement before. So remember we talked about how every day my displacement is 0. So I travel to work, then I travel home from work and have a total displacement of 0. Where my actual distance is different than that. So my total distance is the integral from A to B of the absolute value of the velocity, dt. So it'll be the same exact calculations, except for instead of minus this triangle, I'm going to go ahead and add it because it'll just make it positive. And we expect a larger answer because we're not removing anything. And we end up with 9.5 miles. Okay, at time 12, is she speeding up or slowing down? So at time 12 right here, is she speeding up or slowing down? And how do we know? So her velocity, to tell us, we have to compare velocity to acceleration. Her velocity at time 12 is negative 0.2, and I'm just reading that off the graph. Her acceleration is 0.2 over 1. Her acceleration is negative, and it's negative 0.2 over 1. Yeah, And so our acceleration is also negative, which means they're both negative. You don't really need to know the numbers, just need to say once they're both negative. It's below the x-axis, the slope is negative. That's good enough. And that means since they're the same, they're both the same, she's speeding up. Because velocity and acceleration are both negative. In other words, they have the same sign. And so, since they have the same sign, she's speeding up. If they're both positive, she'd be speeding up. If they're both negative, she's speeding up. If they're different signs, then it's different. So like if they're going like this. Sorry, I have on my eraser. So if they're doing this, she's slowing down. But since they're both either going the same direction, then they're helping each other. Think about it like acceleration versus, so you've got like the wind pushing on you while you're trying to go against it, that slows you down. But if they're both going the same way, you speed up. And then number 6, what was Whitney's average velocity on her journey? Do you think this is a measure of how strenuous, accurate measure of how strenuous she was pedaling? Why or why not? So average velocity, that's, we talked about this the other day. This is going to be the average of the net distance. Or you don't need to do it this way. You can actually just do, since we do all the math, this will end up being S of B minus S of A over B minus A, which is really cool because it ends up doing that for you. And we already know the top is 6.5 over 24. And so that's approximately 0.2708 miles per minute. And no, because she's backtracking, and this is included. So if we wanted to know whether she's strenuously pedaling, we'd need to do total distance with the average of total distance instead, and then we'd be able to tell. Okay, so we're almost done with the time limit on this video, so we're going to go ahead and fill out this box. I'll leave it here. This is where I'll end the video, so you can, of course, pause right here. I'm going to talk about it right now, and then we'll be done because we'll be out of time, and we'll do the other together in a minute. Connecting position, velocity, and acceleration using integrals. Given velocity and position, the integral from a to b of v of t to t is the change in position, net distance, or displacement, or s of b minus, or the final position, initial position, change in position. And then total distance traveled, we need to do the integral of the absolute value, which will take away any backtracking that happened. So again, take the minute, pause the video, and I'm done, and we'll talk about the checking for understanding in the next video.